Hello, Chem 115 students. Another conversation about exo and endothermic reactions and how the heats of reactions are calculated, where it comes from. Exothermic and endothermic reactions. You've heard about these a couple times, but exothermic reactions literally mean that there's excess energy released in the process. The energy that's released comes from forming bonds, but you have to add energy to break bonds. So it's a question of how much of each there is in the process. And so when it's exothermic, the energy of bond formation is greater. One example of a reaction that's exothermic that should be conspicuous that you might have heard of perhaps is combustion, burning in other words. So something like methane, which is CH4 burning in oxygen, what you do with the Bunsen burner, makes CO2 and water, and heat is a product. Heat and light are commonly given off in a combustion reaction like this. There are two ways to represent this. Heat is a product, and you can list a specific number of kilocalories in the reaction equation to reflect that. The other way to do it is just to state the chemical reaction, where the methane with oxygen reacting to make CO2 and water, but the delta H value, the heat change, enthalpy change, is listed separately. When it is an exothermic reaction, you will see that the delta H values are always going to be negative. And that's a very important clue to pay attention to. So exothermic reactions, negative delta H. Now, what about when we look at this in terms of a graph? This looks like something you've seen in your POGIL book, I hope. The exothermic process has products that with a lower energy than do the reactants. And so the overall energy change is a negative sense. So the energy change from the reactants to the products is going down. And that's why we have the delta H is less than 0. Small, again, negative value. Heat is a product, and that negative value corresponds to the heat change for an exothermic process. And you can reflect it by putting it on the product side of the reaction, or you can list delta H separately. Notice that when heat is a product in the reaction statement, you always just list it as one more thing in the list of things, and everything in a reaction equation has a plus sign in front of it. So it's adding to the product list a value for heat. When you list it as delta H separately, delta H is given a negative value when it's an exothermic process, heat released. Chemistry could be considered as delta H negative as well. Gives off heat. Exciting. Now, an example of an exothermic process that we have had a chance to talk about before is the thermite reaction. We saw a video for this in class recently, if I'm not mistaken. And the thermite reaction is one that's so exothermic that it is hot enough to have molten iron as a product. And it's aluminum reacting with iron 3 oxide, making aluminum oxide and iron. Another example of delta H negative. Not telling you how many kilocalories here, but we know that it's a negative value. Another exothermic reaction that's shown in class was the reaction of sodium with chlorine to make sodium chloride and giving off lots of heat. Again, exothermic. And so for this process, delta H is going to be which sign when it's exothermic? Less than 0, negative sign. Now, endothermic process, the other kind of thing, where reactants are going to have a lower energy than the products. The energy of the products is getting greater, and so the change in energy from reactants to the products is going to be an increase, and this means that delta H is positive when heat is going up from reactants to products, being increased overall. So if heat is being gained overall, heat is a reactant in an endothermic process. And when that's the case, you can list the heat on the left side of the arrow as a specific number of kilocalories if you know what it is. Or the alternative is to list delta H separately from the reaction equation and specify the number of kilocalories. But when it is an endothermic process where heat is a reactant, heat is required, then you list it as a positive value for delta H. Two different ways to represent the same idea depending upon how you run into them. All right, So there you have heat as a reactant, or you list it separately and delta H is positive for an endothermic process. Let's think of a specific example. If potassium is added to water, it's a very exciting reaction, and it's contained in a beaker, the reaction that's described in this reaction statement is going to occur where potassium solid reacts with water, and you have a liquid water, surprise, surprise. You make potassium hydroxide, which is going to be aqueous, and hydrogen gas. Oh, nice little bubbles. And the beaker feels hot to the touch, is the statement in this question here. What does that tell you? Does that tell you that energy is being released or being absorbed? Energy is being required or released? Well, when it's getting hot, when you add something, that means that heat is being released. So that would not be an endothermic process. Cross out those two choices. And so one of the other two must be true. So for an exothermic process, such as this, which is true for the sign for delta H? Is it going to be negative or is it going to be positive? As you should have heard once or twice by now and need to remember, an exothermic process will always have a delta H value that is less than 0. So the third answer is correct and the fourth one is incorrect. Here's another example of how we'll use that delta H in these equations. Delta H is a heat change for numbers of moles expressed as shown in a balanced equation. The amount of heat is therefore obviously going to be dependent on the amount of a reactant present, and in this case methane, that is burned. The amount of heat released depends on how much methane is used. And so we think in terms of moles, which we kind of haven't talked about for a little while. And so in this case, you have 1 mole of methane reacting with 2 moles of oxygen to make a mole of CO2 and 2 moles of water. And that produces 213 kilocalories for each of those numbers of moles. Which is why when you describe a delta H below here, you say it's going to be negative 213 because it's released heat per mole as shown in the balanced equation. So what would we do if we have 2 moles of methane reacting? This becomes another unit conversion problem. So 2 moles of methane. Well, think about the kilocalories per mole shown in the second part of the reaction statements here. So put it into your equation, 213, or your calculation, 213 kilocalories per mole of what? Well, look in the balanced equation. The balanced equation has 1 mole of methane. So that's what we want to use for this particular calculation. And so you put your 1 mole of methane in here, and 2 times 213, you might even do that without a calculator. And paying attention to your units will verify that the moles cancel. And 2 times 213, I would bet you can agree with me, that should be 426 kilocalories for 2 moles of methane reactant. All right. Now, what if we are instead using 2 moles of oxygen? Well, 2 moles of oxygen is exactly what's shown in the equation here as well. So it's 2 moles of oxygen is our given. And this time the conversion factor will be the 213 kilocalories per how much oxygen? Well, we're given 2 moles of oxygen in this question, but the 213 kilocalories in the reaction is corresponding to 2 moles of oxygen reacting. Oh, well, then it just cancels out. So there's not a whole lot to think about here. And if you want to be complete, you finish writing it down, but the moles of oxygen and the value of 2 will cancel out, and the answer is simply 213 kilocalories for 2 moles of oxygen reacting. All right, that wasn't so bad. No need to worry about sig figs in this reaction, in this particular statement. We'll let that one be. All right, chemistry is exciting. Gives off heat. Now, this relates to energy values of fuels, just for your information. It's kind of interesting to think about the comparisons here. If you wanted to figure out the most efficient fuel to use, you could look at these energy values in terms of kilocalories per gram of the fuel. Well, let's see, what do we mostly use? Do we use wood? Do we use alcohol? Do we use coal or crude oil or gasoline or hydrogen? Well, we use natural gas, we use gasoline, sometimes we use wood. But obviously, the natural gas and gasoline are pretty good compared to wood. And however, if we could use hydrogen for a fuel, boy oh boy, would that give us a lot of kilocalories per gram. However, the grams of hydrogen are always very small because hydrogen is a very lightweight gas and it has certain problems with explosions if you try to store it and so forth. So it's not exactly the most simply used fuel these days. Engineers are working on this, but that's not yet totally been resolved. All right, a couple more thoughts. Not much more to show you here, but we're getting there. Heat can be written as a reaction for an endothermic reaction, hang on to that thought, or a product if it's an exothermic process. Every exothermic reaction is going to be releasing heat to the surroundings, and the value of delta H for those is always going to be less than 0. An endothermic reaction absorbs heat from the surroundings with a value of delta H that is positive. When we're calculating heats of reaction, the delta H, the enthalpy change of a reaction for a given amount of reactant or product, is going to be calculated based on the delta H for a reaction as specified. We will again use mole ratios, sometimes molar masses, and moles per kilocalorie or kilocalories per mole to calculate heats for reactions. Let's try another example. If you're looking at the reaction of nitrogen and oxygen to make nitrogen dioxide, nitrogen dinitrogen oxide in this case, it has 39 kilocalories listed on the reactant side, so in this case heat is required. And the question posed is how much heat is required for 150 grams of N2O, which is laughing gas, dinitrogen monoxide. The molar mass is conveniently provided for you to make your life simpler and save us a little bit of time. So the reaction shows 39 kilocalories for moles of things as shown in the reaction, as stated in this reaction equation. So in order to do anything, we'll have to go from grams of N2O to moles. Well, when you want to go from grams to mole, think back to stoichiometry. What should we do? Well, I guess the grams better go on the bottom here where they can cancel out grams of N2O per mole on the top. And the molar mass is the value that is stated with units of grams per mole. In this case, we'll call it exactly as shown here, 44.02 grams of N2O per mole. Now, we're not done yet. That's moles of N2O, of course. And so looking at your units, you should be able to notice that the grams of N2O are canceling. Now we're going to need to cancel out the moles of N2O and get ourselves closer to figuring out heat. Well, what is the heat going to be measured in? Look up at your reaction equation and hopefully you'll see kilocalories. So that would be the unit that we're going to use in this particular question. Once in a while you'll see a different one, but kilocalories are fine. And so it's 39 kilocalories per how many moles of N2O? Well, back to the balanced equation. This time it's only that many kilocalories for 2 moles of N2O that is formed. So you can look at your units and recognize that the moles of N2O should cancel out, and you will have kilocalories for your answer once you pull out your calculator and determine the mathematical value. If you do like I do and you want to save yourself a step, you can put 2 into 150 and you can call it 75 on the top times 39 divided by what remains then is 44.02, and I plug a number into my calculator and I get, I hope you tried it too, 66.45. That's enough digits for now, and let's think about how many should be in our answer. How many do you want for this value? Well, we've got 39.0 kilocalories, and we had 150 grams of N2O. Well, that 150 grams is seriously only 2 sig figs, and so that's going to limit our calculations here. In spite of the fact that the kilocalories were provided with 3 sig figs, you end up going with the one that has the fewest. And so for this question, a 2 sig fig answer would be sufficient, and that would be 66 kilocalories for the 150 grams of dinitrogen monoxide. All right, let's try another one. What about this time? This is my last example for today. How much heat is going to be required to react 115 grams of nitrogen? Well, we'll start with our 115 grams, and the molar mass of nitrogen is provided because that's what we'll be using to relate to the kilocalories, because it's always going to be relating to somebody's moles. So 115 grams of nitrogen, we want to cancel out grams, so put the grams on the bottom, and the 28.02 grams is going to be correlating, of course, to, what is it, 1 mole? Sure. 1 mole of nitrogen. And what's going to cancel by the time we've gotten this far? Looks to me like grams of nitrogen. And we're not done yet. We want kilocalories. We want heat. And if we're looking at what comes next, the moles of nitrogen has to cancel out because it won't be in our answer. And so the moles of N2, oops, my tool doesn't like me today, will be on the bottom, but we're relating it to kilocalories. Again, it was 39 kilocalories required. Doesn't matter when in terms of this calculation, but it's required. For how many moles of nitrogen? Well, look back to your balanced equation. There's a 2 in front of that value, so put 2 in front of the moles of nitrogen in the calculation. And now we only need to verify that the moles of N2 cancel, and the rest becomes a calculator exercise. But notice that when we are finished, the unit's going to be kilocalories, which is a value for heat. That's desired. Good. All right. Time to put a pause on this and find your calculator. So putting the value in the calculator, I get a number. My number looks like 80.0321. Well, that's more digits than we want. We don't need that many digits. That's be very uncommon. So how many sig figs belong in this answer? Go back to your original question and double check. We have 115 grams of nitrogen. Oh, that'd be a 3 sig fig value. And the coefficients in the balanced equation will never limit your sig figs because those are counted values. The other value provided here is the delta H, the heat value, per mole is stated again with 3 sig figs. So that looks to me like we should end up with a 3 sig fig answer. How many digits are on your molar mass should be at least as many as you're given in the question, so 4 digits there is good. So reporting this value to 3 sig figs, not too tricky this time, is 80.0 kilocalories. So there's an example of how you determine your kilocalories per some amount of a reactant in a given equation. All you have to be provided is the delta H value in this particular case. You could have listed it separately, and delta H would have been 39 kilocalories per mole as shown in the balanced equation. Be careful about looking for coefficients in the balanced equation, and remember to use molar masses every time you are given grams and need to be able to relate to moles. Enough for today. Good luck with your various assignments. We'll see you in class.